Hi everyone. So today we're going to learn about the next chapter, the introduction to titration. And this chapter is chapter 7. So here is the content of this chapter. The first one is equilibrium. Second one is Le Chatelier principles. Next, the introduction to titration. Next is the types of titration. So here you can see the words titration is actually comes from the titration method. Next is titrant and titrant. So you can see a difference between these two terms. And the last one is the volumetric calculation. So basically for the calculation, most of the calculation you already learned in chapter 1 and also during the lab session. So now we go for the first subtopic, which is equilibrium. Okay, in this, in any chemical reaction, we must have a reactants and also a products. Okay, so basically for each reactants and for each products, there will be a what we call as a stoichiometric coefficient. Okay, which is represent as the small letter of A, B, C, D. Okay, so what we can understand from the equilibrium. Okay, so by referring to the chemical reaction, we can say that the forward rate of reaction equals to the reverse rate of reaction. So for you to easy to understand, the meaning of equilibrium is actually the chemical reaction is complete and it stopped to react. So now when we can find out that the chemical reaction is at equilibrium, so we must convert from the chemical reaction into the mathematical equation so that we can easily to identify by using the calculation. Okay, so here you can see K is actually the equilibrium constant equals to products divide to reactants. So here you can see for each of the reactants and products is represent and located in the bracket. This bracket is actually represent the concentration of each reactants and each product. And you can see also the small letter is actually represent the stoichiometric coefficient, also involved in the mathematical equation. So now consider a real chemical reaction. Consider this chemical reaction N2O4 in a gas phase convert to 2 mole of NO2 in a gas phase. Okay, so from this chemical reaction, how you can write the correct mathematical equation. So here you can see Kc equals to NO2 to the power of 2 divide N2O4. So we implement the concept and the theory of the equilibrium in this chemical reaction. Instead of that, we also have Kp. Kp is actually comes from the words equilibrium constant by using the partial pressure as the parameter. Okay, so here you can see the same way, the same method that you use to write the mathematical equation, even though it used the partial pressure for each reactant and product. And basically, this partial pressure, we will implement the ideal gas law, which is PV equals to nRT. So you can see that when we have uh, any reactants or product that was in a pure solid or pure liquid phase, so we will negligible the value. Okay, so you need to look very carefully the phase of the reactants and product. Okay, so now we're going to the heterogeneous equilibrium. When we talk about heterogeneous equilibrium, we must understand first the homogeneous equilibrium. So when we talk about homogeneous, it means that the chemical reaction uh, contained with reactants and product in the same phase. However, for the heterogeneous equilibrium, the chemical reaction does involve a different phase of reactants or products. Okay, so let's consider this one example. Calcium carbonate in a solid phase degraded become calcium oxide in a solid phase plus with carbon dioxide gas. So the way we write the mathematical equation is actually K equals to the concentration of CO2 only. Why? This is because we negligible the concentration of calcium oxide and also calcium carbonate due to the solid phase. Next is the Le Chatelier principles. In any mathematical equation, there must be a principles. So in this equilibrium formula, we implement the Le Chatelier principle. So when we talk about Le Chatelier principle, it's actually about when a change is applied to disturb a system at equilibrium, the reaction will favor to reduce the effect of the change. So what you can see here is actually when the system at equilibrium and then we disturb the equilibrium and then the equilibrium will counter back the effect of the disturbance. Okay, so here we can identify three factors that affect equilibrium systems. The first one is temperature, second one is pressure or volume, and the third one is the concentration of reactants or product. Now let's look for the first effect of concentration. Okay, so the first factors, okay, about the concentration. Okay, so here you can see one example like from the nitrogen gas plus with 3 mole of hydrogen gas to produce ammonia gas. Okay, so the way we write the mathematical equation, K equals to ammonia to the power of 2 divide with N2 multiply with hydrogen gas to the power of 3. So basically, when we try to identify the effect of changes when the disturbance is implemented in the system or disturbance is enter the system at equilibrium, so we will use another equation or another terms. Here you can see it represent Q. So basically, what is the difference between K and Q? Q is actually we use the products and the reactants concentration uh, at initial or original and okay not after the reaction occurred. Like for K is actually we use the value after it reach equilibrium, after the chemical reaction stop complete. Okay, so in this you can see the Q terms is actually we refer to the original concentration or initial concentration. So what we can say about the differences between K and Q? So by the time you calculate the value of K and value of Q, you must compare both value. Like here you can see when Q equals to K, you can estimate that the system was in equilibrium. Okay, so when Q is greater than K, so the system will shift to the left. Okay, however, when Q is less than K, the system will shift to the right until Q equals to K is achieved. Now we go for the second factor, the effect of temperature. So basically, when we focus on the system or chemical reaction, like for endothermic or exothermic process, endothermic process does involve the rise of temperature in the system. So when the temperature increase, the Kc value also increase. However, for the exothermic reaction does require um, uh, um, low temperature because the system is actually release a certain amount of heat to the surrounding. So when the heat is releasing, so you can see that the temperature will be decreased. Hence, the K value will be decreased. Now let's look for the third factors, which is the effect of catalyst. As you all know, you already learned about catalyst during your school. Catalyst does not take part in any of chemical reaction. It just help the chemical reaction to speed up or to become faster. Okay, so a catalyst does not change the direction of reaction of Kc value, and also it will not change the equilibrium constant. It does change the rate of reaction only. Okay, so now let's look for the introduction to titration. What you can identify as a definition of titration is a method to determine the quantity of a reagent. In this case, the reagent is a known concentration. A method to determine the quantity of a reagent required to react with a known volume of sample. And as you know, when we have a sample, it means that we still don't know the concentration of our analytes in the sample. Okay. Here is the types of titration. We have three types. Okay, the first one is the volumetric titration. This volumetric titration is actually comes from the word volume. So the signal is volume. Here you already learned during the lab session. By the time you use the burette and you have your titrant and you have your sample and you have your indicator. That is what we call as volumetric titration. Okay, so volumetric titration involves calculating the amount of sample by a known volume of standard solution until the end point. Okay. Second is gravimetric titration. In these types of titration, we refer to the mass as a signal. The mass of the product after the chemical reaction complete. Okay, so we can see by the time we weigh the mass of the product, we can identify the amount of our analyte in the real sample. Next is the colorimetric titration. The colorimetric titration is actually we use the electrical current as the signal. Okay, so this signal consumes the analyte, so we can identify the total amount of analytes in the real sample. Okay, before I go to the next slide, so I just want to mention that the titration is actually comes from the words titration method. Next is the types of volumetric titration. So we have a few types of volumetric titration, and here is the few examples. Okay, the first one is the acid base or neutralization, and I believe certain of you already learned about the acid base titration during our lab session. Next is the precipitation. The precipitation is actually we focus on the mass that produce after the reaction complete. Okay, so this is more towards the precipitation titration. Third one is the complex formation. These types of volumetric titration is actually referring to the um, metal as our analytes and surrounded by the ligands to produce a complex. Okay, so the next one is oxidation reduction, or so-called as redox process. So here is the common terms used in titrimetry. Okay, standard solution. What is standard solution? A reagent of known concentration used to carry out a titrimetric analysis. The first properties of standard solution is it is a mass known concentration. If it's not, if you still cannot identify the concentration, so that is not a standard solution. Next is equivalent point. Equivalent point is a point in a titration when the mole of titrant is equivalent to the mole of analyte. So here you can see, and the titrant is actually in the burette. Okay, the titrant words end with T is actually the solution that contained in the burette. Okay, so here what we can see, equivalent point is actually when the reaction is complete. Okay, so it will give a signal. Okay, um like the color changes. Okay, so you can identify this especially in the acid base titration. Next is the back titration. So in this technique, it does involve the excess of reagent used to neutralize the sample is determined by a titration with a second reagent. Okay, so I can say that back titration is a very good method in order to reduce uh, the human error. Okay, so we can use the back titration, okay, to remove the excess of reagent that we use during the first titration. Endpoint. So when we talk about endpoint is actually by the time you see the change of color in the sample solution after titration, we can estimate that that is the endpoint. However, endpoint is commonly we call as the range of uh, volume. Okay, we can estimate a point. It is a range of points. Okay. Okay, next is the titration error, the difference between the equivalent points and the endpoint. So this is the things that we need to include by the time we do the titrimetry. So here you can see that the error the titration error equals to the actual volume of reagent minus with theoretical volume to reach the equivalent point. So you can simply use this formula by the time you do any kind of titration to identify the titration error. Next is the indicator. So as you all know, indicator is we use indicator to make us easier to identify the endpoint. Okay, so reagent, it is a reagent added to the analyte solution to produce an observable physical change, so called the endpoint at or near the equivalent point. Okay, next is the primary standard. Primary standard is the ultra-pure compound that is used to determine the concentration of the standard solution in volumetric and mass stoichiometric method. It is an ultra-pure compound. Okay. However, for the secondary standard, it is a less pure compound whose composition is reliable, known, and serve as reference material for the trimetric method of analysis. Both standards can be used. However, most of the standard that we use is actually the secondary standard. Okay. Okay. What are the requirements for primary standard? The primary standard must have a highest purity, good stability, high solubility, high formula weight, easily available at reasonable cost, free from hydrated water and unable to absorb moisture. Okay, so this is a few properties or requirements for primary standard. By the time you want to choose what is the standard solution, we must focus on these three types of properties. The first one is it must be stable. Okay, it must not easily degraded or easily become reactive. Okay, it must be stable. Second is react rapidly and completely with the analyte. Okay, so it must be uh, what we call as a that it doesn't need any other catalyst or any other chemicals to react first and then it react with analyte. No, okay, so it is better that the standard solution complete react directly or rapidly, okay, and completely with the analyte. The third one is undergo a selective reaction with the analyte, so it must be selective, okay, selective towards the analyte. So here is the apparatus of volumetric titrimetry. So as you all know, we must have a burette, we must have a retort stand, the conical flask to contain our sample, and also an indicator. By the time we want to measure the volume in the burette, you must be careful that we need to read very carefully. Okay, so you need to look very carefully at the lower meniscus. Okay, so here the reading is actually 21.5 milliliter. So this is the technique, the correct technique when you do a titration. Okay, so basically we will do the titration just like what you see in the picture, and then you make the conical flask swirl to make it homogenized. Okay, now let's look for the titrant and titrant. Okay, so we have these two terms, okay, in titrimetry. So what is that? Okay, so in this titrant and with T is a solution containing another reagent. Okay, so this is basically in the burette. However, for the titrant and with D, this solution is actually allow them to react. Okay, this is the place where them mix together. Okay, to have a complete reaction. Okay, so in here you can see in a acid-base titration, it can be both. Okay, either it is a acid or base. It can be either. Okay, so just like what you did in the lab session, we can see that the base is in the burette, I guess. Okay, I don't remember. And in the conical flask or the titrant uh, is acid. Next is complex sorbitrate titration. So this is for the metal liquor composition. We will learn a lot about this in the next chapter. Okay, so for this, basically in the conical flask or the titrant must consist with metal, and in the burette or titrant must consist of ligand solution. Okay, next is the redox titration. So the redox titration is basically is a oxidizing or reducing agent. It can be both. Okay, it can be any. Next is the precipitation titration. So you must take note that it can be the titrant form a precipitate. So this is the basic formula for you to calculate the by using the volume. So I believe that you already know all this formula, and actually you already learned in chapter 1. So you must know how to calculate the number of mole. So basically you can see that basically, as you can see, they use millimole unit, okay, because this is just to make things easier to calculate the number of mole. Basically they will use the millimole unit, okay, to calculate the amount of analyte. So here is the example of calculation. Okay, so basically for the volumetric calculation, most of the calculation you already learned in chapter 1. So you can simply refer to chapter 1. So here, for example, a 50 milliliter portion of hydrochloric acid solution required 29.71 milliliter of 0.01963 molar barium hydroxide to reach an endpoint with bromocresol green indicator. Calculate the molarity of the hydrochloric acid. So here you can have the molecular weight of the atomic weight of barium and chloride. Okay, so first of all, you need to consider the chemical reaction, and you must balance the chemical reaction first. Okay, so after that, you need to calculate the number of mole involved that makes the reaction complete. Okay, and after you calculate the number of mole, and then you simply divide with the total volume of the uh, hydrochloric acid plus with barium hydroxide. So in this case, it will be 50 milliliter plus with 29.71 milliliter. Okay, and then you will get the concentration of hydrochloric acid. Okay, so another example. A 100 milliliter sample of brackish water was made ammoniacal, and the sulfide it contained was titrated with 16.47 milliliter of 0.02310 molar silver nitrate. The analytical reaction is as follows. Calculate the concentration of H2S in the water in ppm unit. So in this example, you must be careful with the question, what they want. You need to give what the question asks. Okay, so here you can see they ask you to calculate the concentration of H2S in the water in ppm unit. So as you all know, 1 ppm equals to 1 milligram per liter. Okay, so basically you will see that you have a sample about 100 milliliter, okay, and you titrate it with this silver nitrate. In this case, silver nitrate is your titrant, a solution that contains in the burette. So first thing, you must calculate the number of mole of silver nitrate involved. Okay, after that, when you get the number of mole of silver nitrate, so you can simply make a comparison, okay, by using the chemical reaction. Okay, so you can easily identify uh, the 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 sulfur 2 minus that has been used in this problem. Okay, so after you get the number of mole for silver nitrate, so you can simply compare, like 2 mole of silver will react with 1 mole of sulfide. Okay, so here H2S is actually we refer to the sulfide in the chemical reaction. Okay, so by the time you can calculate, you compare the amount of mole. Okay, so after that you can get the number of mole of sulfide. Then after that, you need to change to you need to divide with the total volume of sample plus with silver nitrate. In this case, the total volume is 100 milliliter plus with 16.47 milliliter. And after that, you get the molar concentration. So in this case, it does not answer yet your the question. So what you need to do is calculate. You need to convert from the mole per liter, change it to milligram per liter. So in this case, you need to have your atomic weight. Okay, so when you have atomic weight, then you can simply multiply it and then you can get the answer in ppm unit. Okay, thank you for your attention. Bye.